All right, we're going to finish up section 22.1, which deals with electrical current. And last time we talked about how we produce electrical current, well, what electrical current is. It's coulombs flowing through a wire or some sort of conductor. It is whenever you have an electric field, it's going to push electrons one way or the other through that field. But the problem is we have to have a way of keeping it going, so we use a battery or a generator. We'll get to generators in chapter 24, chapter 25. But, excuse me, that's not coronavirus, just clearing my throat. What we're going to do today now is look at how we start controlling current, because it isn't enough just to have it flow. And so I want to introduce you to the concept of resistance. Now, resistance means exactly what it sounds like it does. You know, if you're watching Star Wars or some movie and it says resistance is useless, resistance means to try and stop something. When electricity flows through any wire, there is something, any conductor, there's something in that conductor that's trying to stop it. We're going to talk primarily about wires. So let me just give you an idea of why what happens happens. A wire is made up of atoms that are fairly close together, and metals are held together, we say, by a sea of electrons. Or electrons, I should have made this larger, I'm sorry. Let's just do it like this. We've got atoms that are fairly close together, and they are actually sharing electrons. We call these a sea of electrons. And basically, if I had an electron here, that electron is going to be kind of moving around through here. Over the course of a period of time, it'll have some spot, but it ends up staying roughly in one place. But if I take and put a positive charge, let's do a negative charge here and a positive charge here, those electrons are now going to be asked to move across here. So let me make this a little easier to see now. Let's just do like this. This electron, rather than working its way around, will now start doing something like this. It's going to try and move through here, but it has to, in a sense, go around the atomic fields. It's got some resistance. It's bumping into those atoms as it goes. And as a result, there's some resistance to that. How much resistance and where does it come from? Well, there are four factors that determine generally the resistance in a wire. The first one is pretty obvious, and that is the length of the wire. And I'm just going to do it this way. The longer the length, the greater the resistance. That should make sense to you, because if I have so much resistance here and I drive that twice as far out, there's going to be twice as much resistance. Second is the width. And this may be a little bit odd, but the wider the wire, the less resistance. I don't know if I fully have a great way of explaining that, but I think of it this way. If I had two tubes, two pipes, and I had water coming through those pipes, this pipe will have much less resistance to the water because most of the water flows without hitting the edges. This one would have much greater resistance. I don't know if that's exactly the reason that it happens with wires, but that's the way I remember it. Temperature. The higher the temperature, the greater the resistance. And that's because when you start raising the temperatures, these atoms start bouncing back and forth, and they effectively cause there to be higher resistance. The electrons are bumping into them more, if you want to think of it that way. And then lastly is the type of material. And basically it goes like this. Silver has the lowest resistance. Copper is next. Gold is next. Aluminum is next. And then iron, and so on. If you work with electronic circuits, they'll either be plated with silver or gold. Gold, because it doesn't rust real well, or it's very impervious to rusting. Copper wire is what's typically used. I have seen aluminum wire, and if you get some really cheap stuff, sometimes you'll find iron wire, but it's very, very rare. Okay? Now, that is where resistance comes from. There is an interesting equation that deals with resistance. So let me go back. We've got current, voltage, power, and now we're going to add resistance. And those four are kind of the big four when we talk about electricity. Current, our symbol is I, the unit is the amp, which is a coulomb per second. Voltage is V, symbol is V, that's joules per coulomb. Power is P, the unit is the watt, which is a joule per second. And resistance is a capital R and has a really weird symbol. It's an omega, and the unit is called the ohm. And by the way, if you're not catching it, ohm, because of omega. The man who first gave us a relationship between resistance, power, voltage, and current was named George Ohm, O-H-M, and as a result, we use his name for the unit. It's a really strange unit, one that I don't even want to try and help you figure out. You can if you want to, but the equation that Ohm found was that if he increased the voltage on a wire, he increased the current. And this is called Ohm's law. And by the way, very important. When I was got my first job out of college and I was working as an electrical engineer, I was working at a company called Rockwell, which is now part of Boeing. And it had, there was a young man who was 6 months, had hired on 6 months before I did. And he was really a nice guy, but very timid and very unsure of himself. And before I got there, apparently he had a reputation for just bugging people and asking them for help and asking them for information. Remember, this is all electronics. His name was Mark Peacock. And somebody showed me a picture that somebody had drawn. And the picture looked like this. It was a stylized peacock. And it had three big feathers. Actually, it looks more like a turkey the way I'm drawing it. And it had here V equals IR. I is equal to V over R. And R is equal to V over I. And underneath it, it said, figure it out yourself. And it would have been very hurtful. Now I just thought about this as a public YouTube video, but it would have been hurtful to Mark. Of course, this was 40 years ago. It would have been hurtful for Mark to have seen this. But what's interesting to me about this picture, and the only reason I show it to you, is this is such an important equation that that's the one that Jay chose. Just if you know V equals IR, everything else flows from that. So what will happen is this. If you know the voltage and the current, that's what resistance is. It's a relationship between voltage and current. So if I was to tell you I've got a voltage of 120 volts and a current of 20 amps, which is very common. This would be household current, most wire that would come to an outlet in your, say, your room, a regular outlet, would be 120 volts and 20 amps. How much resistance? Well, 120 volts divided by 20 amps, and this would be 6 ohms. The wire would have to have 6 ohms of resistance in it. You say, well, what would happen if the resistance dropped? Well, then you would have more current flowing. In fact, let's say that we had the same thing, but we had 120 volts, But for some reason, our resistance dropped from 6 amps to 0.6 amps. How much current would there be? Well, now we're using this equation. I is equal to VR, and this would be 120 volts divided by 0.6 amps, and this would be 200 amps. By the way, in your house, you have a